Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 31 and the lecture topic is DIBL, which is Drain Induced Barrier Lowering, GIDL, Gate Induced Drain Lowering, Channel Length Modulation and Source Drain Series Resistance. So, this lecture will be primarily involved with all the short channel effects which a MOSFET works, because after this we will be going for a double gate MOSFET. It will be there where all these concepts will come into picture. It does work at very low short channel. So, the channel dimensions are very small. These effects are more relevant or prevalent in those dimensions. So, with this let me showcase to you what the, so we will be doing this class number 2 here, and the outliner will be looking into the short channel effects. We will be then coming to 2-dimensional potential plot in a MOSFET, right. This is a simulated potential plots which is available to you in a MOSFET. We will look into DIBL, drain induced barrier lowering, and gate induced barrier lowering. We will come to channel length modulation and finish the discussion on source drain series resistance. Now, let us look at the short channel effect. So, what was the idea here is that when the channel length, when you reduce the channel length, right, and it becomes very small, then we define that to be as the channel defined as the channel length, short channel length. Try to explain to you. I will show to you how does it work out. So if this is my dimension of the device, so this is my n plus p n plus. Now, there will be a depletion region here and there will be a depletion region here even without applying any bias, right. This depletion width we can refer to as XD0, and this is basically the depletion width under no bias condition or zero bias condition. Now, as you start reducing the dimensions of the channel, right, and you make the channel length smaller, which effectively means you try to bring the source and drain closer to each other, then what happens is that the effective channel length which you get is L, which is the channel length, minus 2 times XD0, where XD0 is the depletion width at this end and this end. Assuming that the doping concentration on the source and drain are exactly equal, we can say that the depletion width thicknesses on the source and drain side are also equal, and therefore, the effective channel length is L times 2D0, one from source, another from drain. However, as you start to make them closer and closer, and this channel length L becomes of the order of approximately 2 XDO, then we say that you have entered into a region where you have short channel lengths, which means that the two depletion widths are very close to each other, right. And therefore, and why do you do it? There are many reasons to do it. One is obviously in design there are 3 components, which is power, we have performance and area. So, this is the very important parameter which we use in a design problem, be it analog or mixed signal design. So, you want to reduce the area. Reduction in area can take place if you are able to scale down the dimensions of the devices. And one way to scale down the dimension of the device is to lower the channel length drastically. Once you lower the channel length drastically, you will see that the effective area reduces, and therefore, the silicon utilization reduces, and you can pack in more number of devices per unit area. Second is that if you lower the channel length, if everything else remains the same, your aspect ratio actually becomes larger and larger, and therefore, your drain current becomes larger. So, at the cost of power, your performance becomes much better. However, when you lower the channel length, you have these problems of short channel effect. So, if you look at this dimension here, this X of XD which you see here is the depletion width within the substrate, right, within the substrate, and you have this LD is the depletion width at the silicon dioxide interface due to drain and the bulk, and delta LS is the source side depletion width which you see, and X of DS is basically the depletion width of the between the source and the substrate. Now, when you apply gate bias here greater than the threshold voltage at this particular point, you have a gate induced bulk depletion layer, which is very true also. Let us assume that your bulk is grounded and you have applied a positive bias. Since this is a p type substrate, you are basically reverse biasing it. As a result, there will be a depletion width which will be there. So, this is basically a gate induced depletion width, assuming that the source and drain are grounded. These are gate induced depletion width, that is the reason it is written as gate induced bulk depletion region here, right. So, as you make your gate voltage higher and higher, this tends to become larger and larger, obviously because you are doing a reverse bias PN junction in a natural way of things. Once you are doing it, you have therefore a large area which is covered by the depletion. Now, if you further increase the gate voltage, there will be, obviously the inversion has already been formed because your gate voltage is greater than the threshold voltage of the device. If you look at junction capacitances here, the depletion junction capacitance and the source junction capacitance, let us concentrate on this part, this circled part, this dotted part. Let me rub the current this thing, and let us just concentrate on this part, on the drain side, right. On the drain side, let us concentrate. Now, if you concentrate on the drain side and if you increase your value of VDS, then the reverse bias increases, and therefore, del LD right will go on increasing, right. And the del LD increasing basically effectively means that there will be reduction in the channel length because of the increase in the value of VDS, channel length modulation effect, right. So, go on increasing the value of VDS, del LD will go on increasing. As a result, your effective channel length will go on reducing. This is one of the components of the short channel effect, clear. So, this is one of the components. So, short channel effects are when you make the source and drain closer, what are the effects which affect the electrical performance of the device is referred to as the short channel effect. With this, let me explain to you in detail what we were discussing. The short channel effect does is that as the channel length is reduced, the threshold voltage also reduces, but this is known as threshold voltage roll off. This roll off takes place with reduced channel length. So, if you reduce your channel length drastically lower and lower, your threshold voltage will roll off. As you can see from the diagram onto the left hand side. So, you are plotting basically the threshold voltage with respect to the effective channel length. When your channel lengths are very large, let us say 2 micron, 3 micron, 4 micron, you can see the threshold voltage is almost constant independent of the channel length. For both N type and P type MOSFET, if you look, if you concentrate in this region, then you see almost they are constant, right. This is they have plotted for linear threshold when VDS is 0.1 and in saturation when you get 3 volts around here, and assuming that my bulk to source or body to source is 0. So, there is no body effect. So, the first graph which you see, the first one which you see, this one is primarily when you keep your VDS to be equals to 0.1 volts, and this is when you keep your VDS to be equals to 3 volts. Now, quite interestingly, if you see when your channel lengths are very large, the threshold voltage is kept constant and almost independent of the channel length, right. It is almost constant which you see, but near about 1 micron and below, you start to see a deviation from the fixed value of the threshold voltage, and the threshold voltage for an N channel MOSFET, for example, starts to reduce as you make your channel length smaller and smaller. Why, we will look into it later on, but that is what is happening. So, when you reduce the channel length, you will have this roll off taking place. Interestingly, the linear threshold roll off, when your VDS is kept at 0.1 volt in the linear region of operation, the roll off is smaller, but if your VDS is larger, your roll off is also larger, right. Because why? Because we will come to that later on when we discuss about the DIBL effects, but typically just for information's sake, that when you are biasing your device in the saturation region of operation, typically at that particular point the roll off much more larger, right. First observation. The second observation is NMOS roll offs are much larger as compared to PMOS roll off, right. So, now what is the consideration as a designer you should have? As a consideration, look at the last statement of this slide, that as a designer you need to understand that you can't let the threshold voltage go down to too low a value, right, because you have applied gate voltages and so on and so forth, and therefore, you need to ensure that the threshold voltage does not become too low for any minimum length channel device in a MOSFET, right. If it becomes too low, then what will happen is that your switching will be better because you have reduced the threshold voltage to a low value. So, even with a lower value of gate voltage you can make the device go from on to off state and vice versa. But the problem which you will face is that threshold voltage is excessively low. Even with a small gate voltage you will be able to switch on the device. So, you cannot keep it off for a larger gate voltage, right. That is one problem. Second problem is that your power will be also will reduce because you have reduced the threshold voltage, but there will be issues here. The second problem which you will face is at such a low value of threshold voltage, inter device there will be what is known as a variability. So, all of us know that when you fabricate a chip or when you fabricate a device, no two processors are exactly the same, they are changing from one process to another process. And the change, if there is a small change, and if because of the small change, say for example the change is in channel length, the threshold voltage change will be so much that you will not be able to match the two devices properly when you are designing it. So, those things have to be kept in mind when you are discussing the short channel effect in a detailed manner. Now, let me come to some idea. I did not bring the slides for it, but let me give you the small idea of what is known as a MOSFET scaling. So, let us discuss about scaling. What is the meaning of scaling? Scaling effectively means that can we reduce the physical dimensions as well as electrical dimensions such that the performance of the device actually becomes better and better. So, scaling basically means if you scaled, as the name suggests, scaling up or scaling down, both the ways you are scaling, you want to reduce the dimension of the device, which means that you need to scale it down. So, when you want to scale it down, you make the device like sort of lowered down in terms of dimensions, and therefore, its corresponding effects on electrical characteristics will be known to us very easily. Dennard was a scientist who gave a very well defined Dennard. So, this is known as a Dennard and is basically known as Dennard scaling laws, right. And what he said was that if you scale by a factor of k your channel length, you reduce your factor by k, what other parameters should change so that you are able to sustain a best performance of the device. So, this was done by Dennard and it was known as Dennard scaling law. Now, there are two types of scaling laws available to us. There are two types of scaling laws. One is known as a constant voltage scaling, and we have constant electric field scaling. So, we have constant voltage scaling and we have constant electric field scaling. I will explain to you each one of them individually. Constant voltage scaling means that you are only scaling down the voltage in a proper sense, which means that if you have some voltage VDD and as you progress in technology you scale it down this VDD by certain factors, right. You scale it down, right. However, there is a problem here that if you just scale down the voltages, say for example, you are reducing the gate voltage, you are reducing the drain voltage and so on and so forth, then you need to also ensure that your threshold voltage also needs to be scaled down, right. For example, if your gate voltage is peak voltage is 1 and you still remain, if your VGS is equals to 1 volt and your threshold voltage is let us say 2 volts, assuming it to be 2 volts, then you will be never able to switch on the device at any point of time. So, just by scaling down the gate voltage will not help you, you need to scale down your threshold voltage also. Similarly, if you scale down the value of VDS, drain to source voltage, if you scale it down, what you effectively do is that you reduce the value of IDS, the drain to source current, right. You reduce it drastically. Why? Because your VDS is reducing. So, if you remember your drain current equation, IDS was equals to in saturation or even in the linear region, it is mu n Cox, right, into W by L into VGS minus VTH whole square. So, if you would have reduced the value of VGS, let us suppose, then the overdrive will reduced and there will be a parabolic reduction in the value of current, which means that your IDS square times R, which is the output power out, will actually reduce parabolically, which is a good idea. But then you lose in performance, because if you reduce the value of current here, right, the amount of time taken to charge the capacitor of a CMOS inverter will be much higher, and therefore, the frequency of operation will actually reduced. You will not be able to switch your inverter very fast. So, though you are gaining in terms of power, you are losing in terms of performance, because your requirements are very high. So, this is what is known as a constant voltage scaling. Let me come to constant electric field scaling. As the name suggests, what we do here is that electric field is defined as voltage by channel length L. So, if you reduce this value of L only, your electric field will increase, right. If you keep your V constant, if you reduce your L channel length and you also reduce your voltage such that the electric field remains constant, then we define that to be as a constant electric field model. So, we have two scaling. This electric field scaling tells you that as you lower the channel length and you lower also the voltages, then voltage by channel length, which is electric field, almost remains constant, which has got a good idea. So, if your electric field is constant, this ensures that reliability of MOSFET is not compromised. Right? And when I say electric field, I mean both horizontal and transverse electric field. So, when I say electric field constant, I mean to say both transverse electric field and both horizontal electric field are constant, and this is what is known as a constant electric field model. So, let me take up one example and show it to you. What do I mean by that? Electric field. So, typically the Dennard scaling law, if you follow, then it is seen that channel length, T oxide thickness, width of the channel, Xj is the junction dimensions, they all scale down by a factor of k. I will explain to you what this k is. Doping concentration Na, Nd, they scale again by a factor of 1 by k. So, basically the doping concentration increases with each passing technology node, whereas the physical dimensions actually reduce by a factor of k. This k is, let me help you out at this stage only, is approximately equals to 0.7. So, when I scale down by a factor of 0.7, it basically means that you are actually reducing it by some value. Then the voltage, of course, is scaled down by a factor of k. Electric field is held constant. The drift velocity is again held constant, right. WD is the width of the depletion region, capacitance and the drain current. This is again by a factor of k, which means there is a reduction in the current, in the capacitance and the width of the depletion region. Device density, device per unit area, is actually changing by a factor of 1 by k square, right. Your power dissipation is no change 1, and power dissipation per device changes by a factor of k, and power delay product changes by a factor of k cube. What is the meaning of power delay product? Power delay product basically means power into tau, tau is the delay, and that multiply if you do, then it changes by a factor of k square. Okay. So, basically that factors of k cube is the change for the PDP, right. Both are you need to see. You need to also look at the delay part, circuit delay. Circuit delay is given as CV by I approximately, and this becomes k. And this k is 0.7 depend upon the technology where you are. So, effectively every time you go from a lower technology node to a higher technology node, or from a, when I say higher I mean a lower channel dimensions. So, let us suppose you have a channel length L of say 1 micron, right, that is easier to understand. Then in the next generation, if you follow one Moore's law or one change, this will be 1 into 0.7, and that is approximately equals to 70.7 micron. Then if you take 0.7 into 0.7, it will come out 0.7 micron, and then you multiply again by 0.7 and so on and so forth. It will become 0.49 or 0.5. So, with each technology node change, you will have a 0.7 drop, but other factors vary like this. So, this has been done quite significantly, and this is your assuming that k is equals to 0.7 for each technology domain. The depletion width, or when you have xd, is given as 2 epsilon silicon V built in plus VDS divided by Q times Na, this thing constant. However, drain current per unit width, this is known as the normalized drain current, is always constant. Why is it constant? Because drain current is reducing by a factor of k, the width is also reducing by a factor of k, and therefore, if you divide the drain current with respect to width, you will get a constant value in terms of drain current. Now, this gives you brief idea about the constant electric field scaling sort of model. See, so what I was discussing earlier was that the threshold voltage will also go down. There will be change in the threshold voltage by virtue of short channel effect when it goes to very low value. I am not going to details of the derivation, but I can write down delta Vt, the threshold voltage change, is given as minus q times Na times x dt divided by Cox into Rj divided by L into 1 plus 2x dt by Rj, right, square root, and then minus 1. Rj is basically the, look at the source and drain region, this radii is known as Rj. If this is drain, this is source, then this radii is known as Rj, right. And x dt is basically the depletion width thickness on the substrate side, this side, x dt. And as you can see here, as the dimension of the device goes on increasing, this L goes on reducing, delta Vt goes on increasing negatively, which means that there is a larger and larger fall in the threshold voltage for low channel devices when the channel length is very, very low. So, you see this is threshold voltage roll off, right. Now, the threshold voltage roll off comes out because that at very low dimensions of channel length, what effectively is happening is that the effective area under the gate is actually reducing. Therefore, you effectively require less number of charge carriers to invert the channel, and hence your threshold voltage roll off takes place in terms of reduction, right. It reduces drastically downwards in a sense and gives you a value here. Now, how do you define del Vt? Del Vt is given as Vt for short channel minus Vt for long channel. Long channel, again short channel I have already defined to you, and that is how it is done. So, which means that if you actually lower down the value of L, an n channel enhancement mode MOSFET will actually convert to a depletion mode MOSFET, will behave like a depletion mode MOSFET. Why? Because your threshold voltage has actually gone down. The threshold voltage is a negative shift, and negative shift primarily means you are moving from enhancement mode to depletion mode, right. And this happens when your channel length goes down in the and becomes a short channel effect is more severe in this case. Now, you can actually do one more thing, that if you plot Vt threshold voltage, right, on the x axis and L on the y axis, and this is in micrometers, and this is basically Vt minus Vfb, the flat band voltage change which you expect to see. Then the graphs which we get for various values of Vsb is something like this. This is the doping concentration which you get, 5 into 10 to the power 16 substrate doping concentration, and the value of the device T oxide thickness is 50 nanometer, right. Your junction depth is 0.5 micrometer, and your VFB flat band voltage, let us suppose, is 5 volts. Then we see that the roll off takes place somewhere below 1 micron channel length. And this is quite interesting, that as the doping concentration of the substrate goes on increasing, the threshold voltage also goes on increasing, and this is correct also. It should be like true, because as the doping concentration increases, less minority current carriers are available, and therefore, you require a larger gate voltage in order to form the inversion layer in the channel. And that is the reason you see that it goes on increasing as you move in the forward direction. Now, we write down in this case delta Vt is equals to Q times Na into x dt divided by C oxide into epsilon x dt divided by W. This is a fitting parameter and depends upon many factors, but let us at this stage is just a fitting parameter, and therefore, you see the change in the threshold voltage in saturation is given by this formula, and therefore, this is sort of a width phenomena. So, as the width reduces, delta Vt increases, which means that as you go towards the lower dimension and you make your width smaller and smaller as per the Dennard's law, the change in the threshold voltage also becomes larger and larger because of the width. So, effective threshold voltage visible to you is a combined effect of width as well as that of the length, and that is what you see in this diagram here in this module here, right. And this gives you a brief idea about how you are able to achieve basic concept of threshold voltage roll off. Now, let me come to a simple numerical problem to showcase what I was discussing with you, that let us assume that I have a MOSFET, right. There is a MOSFET available with me, and this MOSFET has got its doping concentration as 10 to the power 19 per centimeter cube, Na as except 10 to the power 16 per centimeter cube, channel length L is equals to 1.2 micrometer. So, we need to find out the punch through potential. What is punch through? When the depletion region of both the sides actually touch each other, we define as a punch through, effectively meaning that your channel is almost lost, right. So, when the if you add therefore the depletion width in the source side and the drain side, and if it becomes of the order of the channel length or is exactly equals to channel length, we define that to be as a punch through. So, what we do in this case is we try to find out the V built in value, and that comes out to be Vt ln of Na Nd divided by Ni square. This comes out to be 0.874 volts. Then you find out xd0. xd0 is basically the depletion width at 0 bias, source drain depletion width, and is given by 2 epsilon s V built in, because Vds will be 0. So, V built in divided by Qna to the power half. This is 0.336 micrometer, and xd will be given as 2 epsilon s V built in plus Vds divided by Q times Na in presence of a charge, in presence of depletion width. Now, in punch through, what will happen is xd0 plus xd should be equals to L. xd0 is the depletion at 0 bias, xd is with bias. If you add the two together, that should be exactly equals to the channel length, and basically the channel length performs worse in this case. So, what we do is that xd0 we have found out to be 0.336. We should get the value, this should be equals to 1.2 micron, because L is equals to 1.2. Therefore, xd happens to be equals to 0.864 volts. Now, just now do a back tracing and place it here. So, what you will get from here is that if you square both sides, then I will get V built in plus Vds to be equals to xds square into Q times Na by 2 epsilon s. Now, all these values are known to you now, just place the value and you get V built in plus Vds equals to 5.77 volts. From there, if you subtract 5.77 minus 874, if you subtract, so you will get some value here, right. So, you will get some value which you will get here. So, this will be 6, then you will have 9, and then you have 8, and then you have 4.864 typically volts, which this will be the value of VDS. So, your drain to source voltage when becomes equals to almost equals to 4.89 volts, you typically have a punch through happening in this case. So, with this, let me thank you for your patient hearing. We will meet in the next class. Thanks.